astronomers accidentally found something that stopped them cold, a galaxy so impossibly large you could line up 160 Milky Ways end to end and still not cross it. But here's the most disturbing part. It had been sitting in existing data for years, completely undetected. Not because it was small, because it was too faint, too massive, too unlike anything their instruments were trained to find. When scientists finally confirmed what they were looking at, they had no explanation for how it got this enormous. Their own simulations had never produced anything like it. Stay with me, because what they found changes everything. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. The year was 2022. A team led by astronomer Martijn Oe at Leiden Observatory in the Netherlands had been doing something deceptively routine, reprocessing existing survey images, looking for faint signals that earlier analyses might have undervalued. No new discoveries were expected. The instruments used were excellent. The sky in that region had already been studied. And yet, as the team assembled the data, a shape resolved itself from the background static that immediately required careful rereading. A galaxy, a single, gravitationally bound structure, stretching 16 million light-years from end to end. 16 million. A light-year is the distance light travels in one full year, roughly 9.5 trillion kilometers, or about 6 trillion miles. In a single second, light covers 300,000 kilometers, 186,000 miles, and completes 7 full laps around the Earth. At that speed, crossing this galaxy would still take 16 million years. When a beam of light first set out from one edge of this structure, our genus, Homo, had not yet appeared on Earth. No human foot had walked anywhere. No human hand had shaped a stone. Every civilization, every discovery, every war, every birth and death that has ever occurred in all of recorded human history, all of it would begin, unfold, and end long before that beam of light finished its crossing. The team named the structure Alcyoneus, after one of the giants of Greek mythology, a titan who fought the hero Heracles for supremacy over the cosmos. The name turned out not to be an exaggeration. To understand why this discovery fractured something in astronomy, we need to understand what astronomers believed before it. For decades, the cataloguing of giant radio galaxies, galaxies whose supermassive black holes fire enormous jets of plasma far into surrounding space, had felt methodical and largely complete. Survey after survey had swept the sky. Roughly 1,000 of these structures had been identified and classified, and across all of that data, a rough ceiling had emerged. The largest known radio galaxies stretched to perhaps 15 or 16 million light-years at their most extreme. Beyond that, nothing. The models suggested nothing much larger was likely. The surveys confirmed nothing much larger existed. Scientists were confident. They were wrong. Not because the universe had hidden something impossible, but because every single survey that had built that confidence, every instrument that had mapped those 15 million light-year giants, had been missing an entire sensitivity regime. Alcyoneus was not discovered with a new telescope, a new mission, or a new technology. Oe's team found it in old data, images already sitting in an archive, already analysed, already considered complete. The discovery was not the result of looking harder. It was the result of looking differently. The instrument behind the discovery was LOFAR, the Low-Frequency Array, a network of radio antennas spread across Europe, with its operational core tucked inside a marshy Dutch nature reserve where mobile phone signals are deliberately blocked to prevent interference. 20,000 individual antenna stations, linked across a continent, functioning together as a single instrument. LOFAR doesn't collect light, it listens. It detects radio waves, electromagnetic signals at frequencies so low that no human sense could ever register them. and converts those invisible signals into images of a universe our eyes will never see directly. On a cold night, standing near one of its antenna fields, there is no drama to observe, just low white shapes in a flat landscape, perfectly still, reading the sky in total silence. And somewhere in the data streaming from those antennas, Alcyoneus had been waiting. The specific survey was called LOTSS, the LOFAR 2-meter sky survey, a systematic mapping of the northern sky at low radio frequencies. What OA's team did was subtle but decisive. They reprocessed the second release of that survey's data by carefully subtracting compact, point-like sources and then imaging what remained at lower resolution. In doing so, they crossed into a sensitivity regime no previous survey had reached for faint, diffuse, extended structures. Picture this. You're standing in front of an enormous mural painted across an entire city wall. If you press a magnifying glass against one corner of it, you will see extraordinary detail in a tiny patch. But the painting's full shape, its true extent, will never be visible from any single magnified view. Earlier radio surveys had operated like that magnifying glass. High resolution, exquisite detail, but a field of view too narrow to ever contain what Alcyoneus actually was. Each survey had captured fragments of its structure and filed them as background, as interference, as nothing. And there was a second problem compounding the first. Alcyoneus's radio lobes, the vast plasma structures erupting from its center, are extraordinarily faint. Not small, vast, but faint. The plasma filling them has expanded across 16 million light-years and thinned to near nothing, like the vapor trail of a single exhaled breath dispersed across a stadium. Most instruments simply were not sensitive enough at the right frequencies to register something so faint and so spread out simultaneously. So here is the unsettling truth that this discovery revealed. For decades, possibly longer, astronomers had pointed instruments directly at the region of sky containing Alcyoneus. The data existed. The signal was always there, and no one saw it because no existing survey combined the right frequency sensitivity with wide enough field coverage to show the structure as a whole. You could have spent a career in radio astronomy scanning that patch of sky and concluded, in complete good faith, that you understood everything in it. Verification took months. The team cross-referenced the LOFAR radio data against two entirely independent data sets: optical observations from the Sloan Digital Sky Survey, which captured the galaxy's stellar core in visible light, and infrared imaging from NASA's Wide Field Infrared Survey Explorer. 3 separate windows into the same object. All 3 agreed. The galaxy's distance was confirmed through spectroscopic redshift, a measurement of how much the galaxy's light has been stretched by the expansion of the universe over the time it traveled to reach us. The result placed Alcyoneus approximately 3 billion light-years from Earth. 3 billion light-years is a figure that requires a moment to absorb. The light we receive from Alcyoneus today left it 3 billion years ago, when the most complex life on Earth was still single-celled. What we are observing is not what Alcyoneus looks like now. We are reading a message written 3 billion years before tonight. The findings were accepted for publication in the journal Astronomy and Astrophysics. Independent teams examined the measurements. The structure held, and then, almost immediately, a deeper question surfaced, one that the discovery had made unavoidable. If an instrument with LOFAR's particular combination of low-frequency sensitivity and wide-area coverage had now revealed a structure that decades of earlier surveys had missed entirely, how many others are sitting undetected in existing archives right now? How many Alcyoneuses are already catalogued as fragments, as noise, in data that no one has yet reprocessed the right way? No one had a comfortable answer to that. And then there is the strangest detail of all, one that the size measurements alone do not prepare you for. In visible light, the host galaxy of Alcyoneus looks completely ordinary. The stellar core, the central collection of hundreds of billions of stars, is a faint, unremarkable elliptical smudge, the kind of object that appears in catalogues tens of thousands of times without comment. Its black hole is not unusually massive. Its star formation rate is among the lowest measured for any galaxy of its type. By every optical measure, there is nothing about this galaxy that announces what it has quietly built across 16 million light-years of surrounding space. The entire structure, the full, record-breaking extent of it, exists in a part of the electromagnetic spectrum that human eyes cannot reach, not hidden by distance, not obscured by dust, invisible by the fundamental nature of what it is, which is where the story truly begins. Because knowing that Alcyoneus exists is one thing, understanding what 16 million light-years actually means, what it would look like to stand at the edge of it, what physics allows it to exist, and what kind of engine at its centre quietly built something this vast, requires us to ask a question we have not yet asked. How large can a galaxy actually get? And what happens when the answer turns out to be something our models were never designed to accommodate? The number 16 million is easy to say. It takes less than a second. But here is what we have not yet done. We have not actually felt it. We have said the words. We have acknowledged the discovery. Now we need to sit with the scale and let it do what it actually does to a mind that takes it seriously. Before 2022, astronomers had a reasonable answer to the question of how large a galaxy could get. The answer had a name, a pedigree, decades of observations behind it, and it seemed, as these things often do when the data accumulates and the models converge, essentially settled. The accepted benchmark was a galaxy called IC 1101, an enormous elliptical galaxy sitting at the gravitational heart of a cluster called Abell 2029, about 1 billion light-years from Earth. Surveys from the Hubble Space Telescope and multiple ground-based observatories had examined it from every available angle. Papers had been published, comparisons had been made. The consensus held that IC 1101 represented something close to the practical upper boundary of what a galaxy could build itself into over the age of the universe. It was the largest known structure of galactic origin. It held that title for years. And then Alcyoneus arrived, and IC 1101, still immense, still extraordinary, suddenly looked like a different class of object entirely. Not because it had changed, because the context had. To grasp what any of these numbers actually mean, we need to begin somewhere familiar, somewhere we know. The Milky Way, our galaxy, the one we live inside, spans roughly 100,000 light-years from edge to edge. That number is easy to say and almost impossible to visualize, so let's approach it from a different direction. The Sun is our nearest star. The next nearest star beyond it, Proxima Centauri, sits about 4¼ light-years away. 4¼ years of light-speed travel just to reach the closest neighbour. That distance already exceeds anything human transportation has ever crossed. Now consider that the Milky Way contains somewhere between 100 billion and 400 billion stars, and the average distance between those stars is roughly similar to the distance between us and Proxima Centauri, a few light-years of emptiness between each one. The Milky Way, at 100,000 light-years across, contains all of that, all those stars, all those distances, all that emptiness, and by cosmic standards, it is a mid-sized galaxy. Not small, but nowhere near the top. A city among cities. Respectable, unremarkable. That is our baseline. Hold it. IC 1101, before Alcyoneus changed the conversation, was the structure astronomers pointed to when they wanted to demonstrate the extreme upper end of galactic scale. And here is where size becomes genuinely complicated, and why astronomers are not simply being evasive when they give different figures for the same galaxy. Picture this. You are trying to measure the size of a city. If you measure only the dense downtown core where the buildings are packed together, you get one number. If you include the suburbs, you get a larger number. If you include every community connected by road and commerce and identity to the centre, you get a larger number still. and if you include the diffuse outer zones where the city gradually fades into countryside, where the light's thin, the density drops, and the boundary becomes a matter of judgment rather than a line, you may end up with a figure that surprises even people who live there. Measuring a galaxy works the same way, and this matters enormously for understanding IC 1101, the galaxy's dense, optically bright stellar body, the part that responds to standard photometric measurement, the visible structure you would see in a Hubble image, spans somewhere between 400,000 and 550,000 light-years. That is already 5 times the diameter of the Milky Way, already staggering, already a number that requires some work to absorb. But IC 1101 also possesses an extended outer halo, a vast, much dimmer envelope of diffuse stellar material that surrounds the bright inner body like the corona around a flame. Measured to the farthest extent of that halo, the galaxy swells to roughly 4 million light-years across. Some estimates, using slightly different boundary definitions and including the outermost tendrils of that diffuse envelope, push the figure towards 6 million light-years. The National Radio Astronomy Observatory itself has noted publicly that this larger figure is difficult to trace back to a primary measurement, a reminder that at these scales, even the boundaries of a galaxy are a subject of ongoing scientific judgment, not a settled line in the data. How do we explain that ambiguity? Not through imprecision, through the genuine complexity of what a galaxy actually is at its edges, where stars thin from thousands per cubic light-year to just a handful, where the gravitational boundary between galaxy and intergalactic space is a gradient rather than a wall, and where different measurement tools, different telescopes, different wavelengths, different brightness thresholds will each return a different answer, all of them correct by their own standards. So let us be precise about what we know. IC 1101's confirmed stellar halo reaches approximately 2 million light-years from its center, giving a diameter of around 4 million light-years by the most careful measurements. That is 40 times the diameter of the Milky Way. If IC 1101 occupied our galaxy's place in space, it would not merely contain the Milky Way. It would swallow Andromeda, our largest galactic neighbor 2.5 million light-years away, without significantly extending past its own measured edge. That is the previous benchmark. That is what the universe, before February 2022, appeared to offer as its largest example of galactic scale. And then Alcyoneus, 16 million light-years, from end to end. Let us work through what that number actually does to the comparison. Take the Milky Way, 100,000 light-years across. Multiply it by 160. That is Alcyoneus. If you laid 160 Milky Ways end-to-end in a straight line, you would approximately span the full length of this single structure. To put that in perspective, if the Milky Way, our home of billions of stars, were the size of a single coin in your palm, Alcyoneus would span the entire width of the room you are sitting in right now. You would also be crossing a distance so vast that light itself, the fastest thing the universe permits, would require 16 million years to complete the journey. When that light first began its crossing, it was the early Miocene epoch on Earth. Ancestors of the great apes were emerging. The Alps and the Himalayas were still mid-construction. Modern humans would not exist for another 15.5 million years. And here is the contrast that stops you cold. The host galaxy at the center of Alcyoneus, the stellar body, the actual collection of stars, has a diameter of roughly 240,000 light-years. Not 16 million, 240,000. That is barely twice the size of the Milky Way. By the optical standard, by the measure of stars, Alcyoneus's central galaxy is entirely unremarkable. You are looking at a structure 16 million light-years across whose source, the engine at its heart, occupies less than 2% of its total length. The other 98% is something else entirely. This is the distinction that makes Alcyoneus categorically different from IC 1101, and it requires a moment of careful explanation. When most people imagine a galaxy, they imagine what a galaxy looks like. A disk of stars, perhaps with spiral arms, or a smooth elliptical glow, something visible, something luminous, something made of the familiar material of suns and planets and space between them. That visible structure, the stars, the stellar body, the thing you would photograph with an optical telescope, is what astronomers call the optical galaxy. It is real, it is measurable, and for most galaxies in the universe, it is the entire story. But some galaxies have a second structure, a structure that exists entirely outside the visible realm. A structure made not of stars, but of plasma, superheated gas launched from the galaxy's core at nearly the speed of light, traveling outward for millions of light years before slowing, spreading, and pooling into vast radio-emitting lobes. These lobes cannot be seen with optical telescopes. They cannot be photographed in any way that would register on a visible light camera. They emit only in radio wavelengths, the long, invisible end of the electromagnetic spectrum, and they can only be detected by instruments specifically built to listen for them. A galaxy with this second structure, a galaxy accompanied by these enormous radio-emitting lobes, is called a radio galaxy. And the true full size of a radio galaxy includes both its optical body and its radio lobes together. This is what IC1101 and Alcyoneus are being compared on different terms. IC1101's 4 to 6 million light-year size is the size of its stellar structure, its stars, its halo, the actual matter it contains. That is a genuine, remarkable measurement of genuine luminous mass. Alcyoneus's 16 million light-years is the size of its radio structure, the full extent of the plasma lobes extending outward from its central stellar body in both directions. If you measured only Alcyoneus's stellar body by the same standard applied to IC1101, Alcyoneus would be a perfectly ordinary mid-range galaxy, unremarkable, invisible in a catalogue. This is what makes the comparison so revealing and so philosophically interesting. Alcyoneus is not simply bigger than IC1101. The two objects are not competing on the same measure of size. Alcyoneus is the largest known structure produced by a single galaxy. IC1101 is likely the largest known stellar body, the largest accumulation of actual stars in the observable universe. They are record holders in different categories, and depending on how you define the word galaxy, you may reasonably consider either of them the largest. Science does not have a clean answer here. The question itself turns out to be more complicated than any record-keeping exercise can contain, but here is what makes Alcyoneus strange in a way that IC1101, for all its mass, does not. IC1101 is extraordinary in ways you would expect an extraordinary galaxy to be extraordinary. Its stellar mass is staggering, roughly 100 trillion stars compared to the 200 to 400 billion in the Milky Way. That is somewhere between 200 and 500 times more stars than our entire galaxy contains. Its central black hole is ultra-massive, estimated at 40 to 100 billion solar masses, against the Milky Way's 4 million solar mass Sagittarius A star. Everything about IC1101, when you measure it by the usual markers of galactic power, is at or near the top of every known distribution. Alcyoneus, measured by those same markers, is not. Its central black hole carries an estimated mass of about 390 million solar masses. That is nearly 1 billion times more massive than our Sun. But by the standards of giant radio galaxies, the class of objects Alcyoneus belongs to, that is below average. Its stellar mass is also below average for this class. Its jet power, the rate at which its black hole is currently firing material outward, is lower than most comparable galaxies. By every measure that astronomers typically use to predict why a galaxy would grow a record-breaking radio structure, Alcyoneus comes up short, and yet it built the largest radio structure ever measured. Astrophysicists worldwide reviewing the data since its publication have arrived at the same conclusion. No existing model fully explains why Alcyoneus grew as large as it did. We know it happened. We measured it with 3 independent data sets. We named it. We published it. We do not yet understand it. And that gap between what we can measure and what we can explain sits at the center of everything that follows. Because understanding the scale of Alcyoneus is one thing. Understanding what produced it, what mechanism at the core of an otherwise ordinary galaxy could quietly build a 16 million light-year structure without any of the extreme properties that should, by every model, be necessary, requires us to look not at the galaxy's size, but at its engine, at what lies at the center, at what it has been doing, likely for hundreds of millions of years, across a distance that makes the entire Milky Way feel like a footnote. The answer involves physics that humans only began to understand in the 20th century, and the structure it produces, invisible, immense, and indifferent to our instruments unless we know exactly what to listen for, turns out to be the key to everything we thought we understood about how the largest objects in the universe are built. The most remarkable structure ever traced by a single galaxy has been sitting in our sky for 3 billion years. Astronomers have photographed that region of sky dozens of times. The images exist in archives going back decades, and in every single one of them, Alcyoneus looks like nothing at all. Most of the universe is invisible, not distant, not obscured, not hidden behind anything. Invisible, because it emits light our eyes were never designed to detect, at wavelengths so different from what our visual system can access, that even our most powerful optical instruments pass over it without registering anything unusual. Alcyoneus is the clearest example of this that astronomy has ever produced. 16 million light-years from end to end, the largest known structure built by any single galaxy in the observable universe. And, in a standard photographic image, its host appears as a faint, featureless elliptical smudge in the constellation Lynx, unremarkable, unnumbered in any catalogue of unusual objects, indistinguishable by eye from tens of thousands of similar objects in the same survey. The full structure, all 16 million light-years of it, is simply not there in the image, and the reason tells us something profound about the limits of human perception and about how much of the universe has been waiting, in plain sight, for the right instrument to finally listen. The light arriving at your eyes right now, from a screen, from a lamp, from whatever source is illuminating the room around you, is electromagnetic radiation. It is energy moving through space in the form of oscillating waves. And the color you perceive depends on the wavelength of those waves, how tightly or loosely they are packed together as they travel toward you. The full range of electromagnetic radiation stretches across an enormous span of wavelengths, from gamma rays, whose waves are shorter than the diameter of an atomic nucleus, all the way to radio waves, whose waves can be longer than a building, a city, a continent. The entire range is called the electromagnetic spectrum. Human eyes are sensitive to an extraordinarily narrow slice of it. The wavelengths we can see, what we call visible light, span roughly from about 380 to 750 nanometers. A nanometer is 1 billionth of a meter, roughly 100,000th the width of a human hair. Our entire visual range spans a difference of less than 400 nanometers. The full electromagnetic spectrum spans a factor of more than 10 trillion in wavelength. Picture a radio receiver that can only tune to a single frequency out of a dial, covering the entire audible range. Not just music stations, not just AM and FM, but every sound that has ever existed at any frequency, from the lowest rumble of an earthquake to the highest pitch a bat can emit. That single frequency is what human eyes represent against the full spectrum of electromagnetic radiation. One channel, one station, extraordinarily good at its job, but capturing only a fraction of everything that is actually broadcasting. Everything outside that narrow band, X-rays, ultraviolet, infrared, microwaves, radio, passes through our visual system without registering, not because it is not there, because we are not built to receive it. Radio waves are not fundamentally different from visible light. Both are electromagnetic radiation. Both travel at the same speed, 300,000 kilometers, or 186,000 miles per second. The only difference is wavelength. Radio waves are simply much, much longer, stretching from a few millimeters to many meters, rather than the nanometer scale waves that produce color and brightness in our eyes. And because radio waves are a form of light, they carry information about the objects that produce them. A radio telescope, essentially a large metal dish connected to an extremely sensitive receiver, does not magnify visible objects. It listens for electromagnetic signals at radio wavelengths and converts those signals into data that can be processed into images. What those images reveal is a universe that our eyes have never seen and can never directly access. Most of what Alcyoneus actually is exists exclusively in that radio domain. When the supermassive black hole at Alcyoneus' center fires jets of plasma in two directions, when those jets travel millions of light years and slow and pool into vast lobes, the material in those lobes does not glow in any wavelength our eyes or optical telescopes would detect. The plasma is not hot enough to radiate visible light. The stars, if there were any at those distances, are too sparse to illuminate it. By every optical standard, the space those lobes occupy is simply empty. But something is happening inside that plasma, something our eyes are blind to, but that a radio telescope reads clearly. The electrons inside those lobes are moving at extraordinary speed, not slightly fast, relativistic, meaning close to the speed of light, moving at speeds so extreme that the rules of classical physics no longer fully apply, and the consequences of Einstein's theory of special relativity become physically significant. Now, those electrons are not moving in straight lines. The lobes are threaded with magnetic fields, invisible lines of force extending through the plasma, created by the same jets that deposited the electrons there in the first place. And when a moving charged particle encounters a magnetic field, the field exerts a sideways force on it, curving its path. Imagine a spinning top on a table. If you tilt it slightly, it does not simply fall, it precesses, tracing a wide spiral as it falls. Electrons in a magnetic field do something similar. Instead of traveling in a straight line, they spiral around the magnetic field lines, following helical paths through the plasma. An ordinary electron spiraling through a magnetic field at everyday speeds would emit only a weak, low-frequency hum of radiation, barely detectable, but a relativistic electron, one moving at close to the speed of light, spiraling through that same field produces something far more energetic. The radiation it emits is called synchrotron radiation, named after the particle accelerators, where physicists first observed it artificially in the 1940s. The name comes from the machine, not the phenomenon. But the phenomenon turns out to be one of the most widespread processes in the universe. Synchrotron radiation is not a single color or frequency. Depending on the energy of the electrons and the strength of the magnetic field they are spiraling through, synchrotron emission can occur across a broad range of the electromagnetic spectrum: radio, infrared, optical, even X-ray, in the radio lobes of giant galaxies like Alcyoneus, where the magnetic fields are relatively weak and the electrons, though energetic, are not the most extreme found in any astrophysical environment. The synchrotron emission falls predominantly at radio wavelengths. Long-wave, slow oscillating signals that propagate across intergalactic space, and eventually, 3 billion years later, arrive at the antenna arrays of LOFAR and register as faint, structured patterns in the data. This is what the images show. Not plasma glowing in the visible range, not stars, not heat, but electrons, countless trillions of them, spiraling through magnetic fields across millions of light years, and producing, through the physics of their motion, a faint radio signature that carries the precise outline of the largest structure any single galaxy has ever built. You're sitting somewhere right now. The light reaching your eyes is navigating a narrow slice of reality with extraordinary efficiency. It tells you distance, color, shape, motion. In the few hundred milliseconds between light touching your retina and your brain constructing a visual scene, you receive more useful information about your immediate environment than any other sensory system could provide in that time. But none of that machinery, not your eyes, not your brain, not the most powerful optical telescope humans have ever built, would show you Alcyoneus. Even if you could be transported to perfect dark sky conditions with the greatest optical instrument ever made, and you turned it to exactly the right patch of sky in the constellation Lynx, you would see a faint elliptical galaxy. Mildly interesting. Catalogue entry number SDSSJ 08142.1.68 plus 5 22410.0. That is all. The 16 million light-year structure surrounding it, the plasma, the magnetic fields, the spiraling electrons, would be completely absent from everything you saw. The emptiness around that galaxy would look like emptiness, and you would have no way of knowing that the space appearing empty around it is filled, in the radio domain, with one of the most extraordinary structures in the observable universe. This is not a failure of our instruments. The best optical telescopes on Earth and in orbit have photographed that region many times. The absence is real. The structure simply does not emit in wavelengths they are designed to detect. What the LOFAR survey revealed in 2022 was not something newly created. Alcyoneus has been there for hundreds of millions of years at minimum, slowly building those lobes, quietly expanding across the intergalactic medium, producing synchrotron radiation the entire time. The signal existed before the telescope, before the survey, before the researchers. Every previous instrument that scanned that patch of sky received nothing, not because it was pointed the wrong way, but because it was listening at the wrong frequency. This is a truth the universe enforces without preference or apology. Most of what exists at the largest scales does not emit visible light. The universe's largest structures, the radio lobes of giant galaxies, the filaments of the cosmic web, the diffuse gas between galaxy clusters, are overwhelmingly radio phenomena, or X-ray phenomena, or phenomena visible only in wavelengths, that required entirely new technologies to access. The visible universe, the one that thousands of years of human astronomy was built on, the one our eyes are tuned to, is a thin, bright layer over a much vaster and stranger reality. Science does not yet have a complete inventory of what that deeper layer contains. Every time a new instrument opens a new frequency window, every time humanity builds a telescope that sees in a wavelength no previous instrument could reach, structures appear that were entirely absent from all prior maps. Alcyoneus was one of them. It will not be the last. And here is the question that the existence of synchrotron radiation raises. A question more important than the size of the lobes themselves. Producing it requires two things working together over an enormous span of time: relativistic electrons and a magnetic field for them to spiral through. The electrons were launched from the galaxy's core. The magnetic fields were threaded through the lobes by those same jets. The emission we detect today represents the current state of a process that has been running continuously without pause for what the data suggests is a very long time. How long, and what does it take to sustain it? What kind of engine, at the center of an otherwise ordinary galaxy, fires jets into intergalactic space with enough energy to fill 16 million light-years of structure, and keeps doing it across a time span that dwarfs every human framework for understanding duration? The answer lives at the very center of Alcyoneus, in the one object in the universe dense enough, powerful enough, and patient enough to have built all of this, a black hole, and what it does to the matter that falls into it. At the center of Alcyoneus, hidden inside what looks in visible light like an entirely ordinary elliptical galaxy, something has been quietly running. An engine, patient, inexhaustible, firing 2 columns of plasma in opposite directions across intergalactic space, for longer than our planet has existed in its current form. Before we understood black holes, we thought the universe's most powerful events required its most violent circumstances. Explosions, collisions, supernovae, something dramatic at the center of the action. The reality turned out to be quieter and far stranger. The most sustained, large-scale energy output in the observable universe is produced not by catastrophe, but by a process as geometrically simple as water draining from a basin. Matter falls in, gravity compresses it, a disk forms, magnetic fields twist and coil, and from the poles of the entire system, 2 narrow columns of plasma fire outward at speeds our civilization has no equivalent for, carrying energy across distances our language has no natural way to contain. This is the mechanism at the heart of Alcyoneus, and understanding it requires us to slow down and look at one of the most elegant and terrifying processes in nature, the accretion disk. Picture this. You pull a plug from the bottom of a full bathtub. The water directly above the drain does not simply fall straight down. Instead, the entire surface begins to rotate, matter swirling inward in a tightening spiral, faster and faster as it approaches the center, until it vanishes through the opening. A black hole's accretion disk works by the same fundamental geometry, driven by the same conservation of angular momentum, the physical law that says a spinning object spins faster as it contracts, the same law that makes a spinning ice skater accelerate when they pull in their arms. Gas and dust in the vicinity of a supermassive black hole cannot fall straight inward. The material almost always carries some rotational motion, and that rotation prevents it from dropping directly in, the same way the water in your bathtub cannot fall straight down the drain. Instead, the gas spirals inward, shedding angular momentum through friction and turbulence with the material around it, gradually losing its outward centrifugal support and drifting closer and closer to the black hole in a flattened, rotating disk. The disk is not calm. Particles collide, magnetic fields thread through the plasma, twisting and stretching as the inner parts of the disk orbit faster than the outer parts. The friction that drives the inward spiral also generates heat, enormous heat. The inner regions of an active accretion disk around a supermassive black hole reach temperatures of millions of degrees Celsius. That is hotter than the cores of most stars. The disk glows, blazing across X-ray wavelengths, across ultraviolet, across visible light, with a luminosity that can, at its most active, outshine every star in the galaxy combined. But it is not the heat that matters most to the story of Alcyoneus. What matters is the efficiency. Nuclear fusion, the process that powers our sun, that powers every star in every galaxy we have ever observed, converts roughly 0.7% of the mass of its fuel into energy. That number is extraordinary by any engineering standard. A single kilogram of hydrogen fused in a star releases the equivalent of roughly 63 trillion joules, enough to power a large city for years. For 4.5 billion years, the sun has been running on that 0.7%. An accretion disk is roughly 10 times more efficient. For a standard non-rotating black hole, the process converts approximately 6% of the infalling mass directly into energy. For a rapidly spinning black hole, one where the event horizon is dragged around by the rotation of space itself, that figure can climb as high as 42%. 42% of the mass of every kilogram of material that spirals into the disk, released as pure energy before it crosses the point of no return. The most efficient power plant the laws of physics permit, and it has been running in some form at the center of Alcyoneus for longer than our planet has existed. Here is where something unexpected happens. Not all of that energy radiates outward as light. Under the right conditions, and physicists are still working out precisely what those conditions are, some of the energy, channeled through the intensely coiled magnetic fields threading through the disk, is redirected, not outward in all directions, upward and downward, along the rotation axis of the black hole, perpendicular to the plane of the disk. This is the Blandford-Znajek process, named for the two British astrophysicists, Roger Blandford and Roman Znajek, who described it theoretically in 1977. The rotating black hole drags the surrounding magnetic field lines with it as it spins, literally twisting the geometry of space around it, a phenomenon predicted by Einstein's general relativity called frame dragging. Those twisted field lines act like a tightly wound spring, coiling and tightening until they can redirect energy along the rotation axis with extraordinary efficiency. The result is a jet. Two jets, one from each pole, narrow beams of plasma, superheated, magnetized, composed of electrons and positrons and likely some protons, accelerated to speeds that approach in some radio galaxies, close to the speed of light itself, close to 300,000 kilometers, about 186,000 miles, per second. At that speed, a jet could circle the entire Earth 7 times in the span of 1 second, cross the distance from here to the Moon in a little over a second, reach the Sun from Earth in about 8 minutes. And yet, even at that extraordinary velocity, building the radio lobes of Alcyoneus, pushing plasma outward to a distance of 8 million light-years in each direction, would take at minimum tens of millions of years of continuous firing. Tens of millions of years. Pause on that. The largest radio galaxies, based on their observed sizes and estimates of jet propagation speeds, carry jet lifetimes measured in the range of tens to hundreds of millions of years. 100 million years of continuous jet activity is not unusual for the largest structures known. 100 million years ago, our planet was in the middle of the Cretaceous period. Dinosaurs had reached their peak diversity. Flowering plants were spreading across continents for the first time. No mammal larger than a small dog existed anywhere on Earth. Humans would not appear for another 99.5 million years. And during all of that time, through the entire evolutionary history of every species that has ever walked, swum, or flown on this planet, a black hole at the center of an unremarkable elliptical galaxy 3 billion light-years away was doing nothing more dramatic than quietly pulling in gas, heating it, and firing 2 jets of plasma outward into intergalactic space, without pause, without catastrophe, without any of the conditions that human intuition associates with building something vast. Just physics, operating patiently, at the edge of what physics permits. If you wanted to build the largest known radio structure in the universe, what would you use? Common sense says the most powerful black hole, the highest accretion rate, the most energetic jets, the most extreme conditions available. If size is the goal, maximum power seems like the obvious requirement. Alcyoneus breaks that assumption completely. The black hole at its center carries an estimated mass of approximately 390 million solar masses, a figure that, stated in isolation, sounds staggering. 390 million times the mass of our Sun collapsed into a single point. Our own galaxy's central black hole, Sagittarius A star, masses only about 4 million solar masses. By that comparison, Alcyoneus's black hole is nearly 100 times more massive. But within the class of giant radio galaxies, the specific family of objects to which Alcyoneus belongs, 390 million solar masses is below average. Most comparable giant radio galaxies host heavier central black holes. Most have more powerful jets. Most have higher rates of energy output. By every metric that astronomers typically use to predict which black holes should build the largest structures, Alcyoneus's engine ranks as unremarkable. How does a single black hole, one that by every measure should be producing a smaller structure than its neighbors, end up building the largest radio structure ever measured? Science does not have a complete answer. Not yet. The data from Martinoi's team, confirmed across 3 independent datasets, tells us clearly that Alcyoneus is the record holder, The data also tells us with equal clarity that its central engine does not appear to be exceptional. Something about its environment, the density of the intergalactic medium it is expanding into, its position within the large-scale structure of the cosmos, the specific conditions it has been embedded in for hundreds of millions of years, almost certainly plays a role. But the precise combination of factors that produced a 16 million light-year structure from a below-average engine remains an open question in astrophysics. This is not a gap in the data. The question has been examined by researchers at Leiden, Oxford, Hertfordshire, and Paris. The answer genuinely does not exist yet. And that absence of knowledge, rather than being a problem, is one of the most important things science can tell us. The universe is still capable of producing phenomena that our best models do not predict. If you could somehow stand, protected, from all forces, simply present as a witness, at the launch point of one of Alcyoneus's jets, at the moment the plasma is accelerated outward, here is what the scale of what you were seeing would feel like. Looking upward along the column of the jet, you would see a beam of glowing plasma stretching away from you in a perfectly straight line, narrowing with distance until it vanished toward a horizon you could never reach in any human lifetime. Looking down, the accretion disk would spread around you in a vast, luminous plain, a ring of blazing, turbulent material so bright that no human eye could bear it, rotating at a fraction of the speed of light, consuming matter and releasing energy at a rate that would take every power station humanity has ever built, running for the entire age of the universe to approximate. And behind you, in the opposite direction along the other jet, that same beam extending away into the intergalactic dark, 8 million light-years in each direction, silent, total, and built not by anything spectacular, but by the steady operation of gravity, magnetic fields, and time. The jets explain the lobes explain the size explains why Alcyoneus broke every record and rewrote every model. But something still does not resolve. Alcyoneus has a below-average engine in an above-average structure, and no one knows exactly why. The leading hypothesis involves something we have not yet examined. Not the engine itself, but where that engine is located. Not the black hole at the center, but the vast, almost invisible architecture of matter and energy that surrounds it, shapes it, and may have been feeding it for longer than our solar system has existed. The position Alcyoneus occupies in the universe, the specific environment it finds itself in, may be the key to everything. And to understand that, we need to step back further than we have stepped before, much further, to the largest structures of all. Before Alcyoneus, astronomers had an answer to the question of scale, a real one, not a theoretical upper limit, an actual observed object, catalogued, measured from multiple angles, studied for decades. The answer had a name, a location, and a history that made everything else in the known universe look small by comparison. For years, the largest known galaxy in the observable universe was not a mystery. Astronomers were not searching for it. They had already found it. IC 1101 sat at the center of the Able 2029 galaxy cluster, a dense gravitational city of thousands of galaxies about 1 billion light-years from Earth. And by every measure astronomy possessed, it was the answer to the question of how large a single galactic structure could grow. Papers cited it, comparisons referenced it. Any discussion of extreme galactic scale eventually arrived at IC 1101 as the terminus, the ceiling, the established fact. Scientists were, if not comfortable with that answer, at least settled. And then, in 2022, Alcyoneus arrived. And the question of what it means for one galaxy to be larger than another turned out to be far more complicated than the record books had suggested. But to understand that complexity, to understand why the comparison between these two objects is one of the most intellectually interesting things astronomy has produced in recent years, we need to first understand exactly what IC 1101 is. not as a data point to be beaten, as what it actually is, because standing next to Alcyoneus in the record books does not diminish it even slightly. IC 1101 is extraordinary in ways Alcyoneus is not, and the two objects, taken together, reveal something about the universe that neither one could reveal alone. IC 1101 sits at the gravitational heart of Abell 2029, a cluster containing thousands of galaxies. A galaxy cluster is exactly what it sounds like, a gravitationally bound collection of galaxies, dark matter, and hot gas, all orbiting a common center of mass. Abell 2029 is one of the densest such clusters known, spanning somewhere between 6 and 8 million light-years from edge to edge. That is already a scale that contains most of what we have been discussing. The entire extent of Alcyoneus's radio lobes would fit inside it with room to spare, and at the exact center of that cluster, occupying the gravitational low point where matter naturally accumulates over billions of years, sits IC 1101. The galaxy's stellar body, measured to the standard photometric threshold, spans between 400,000 and 550,000 light-years. That is already 4 to 5 times the diameter of the Milky Way, already one of the larger stellar structures known. But IC 1101 also possesses a vast, diffuse outer halo, an envelope of ancient, loosely bound stars that extends approximately 2 million light-years from the galaxy's center in every direction, a full diameter, halo to halo, of around 4 million light-years. 4 million light-years. That number requires its own translation. The distance from the Milky Way to the Andromeda Galaxy, our nearest large galactic neighbor, the destination we know will one day collide with us in about 4 billion years, is approximately 2.5 million light-years. If IC 1101 occupied our position in space, its outer halo would extend well past Andromeda in every direction. The Triangulum Galaxy, the Magellanic Clouds, every member of our local group, the roughly 50 galaxies that constitute our immediate cosmic neighborhood, would be submerged inside IC 1101's outer envelope. All of them gone, absorbed into the diffuse edge of one galaxy. Now consider what fills that space. The Milky Way contains somewhere between 100 billion and 400 billion stars. That is an enormous range even within its own uncertainty. But take the midpoint, and our galaxy holds perhaps 200 to 300 billion suns, each one a nuclear furnace, each one potentially circled by planets, each one by itself a system of staggering complexity. IC 1101 contains approximately 100 trillion stars. 100 trillion. That number is stated easily. Absorbing it is another matter entirely. Feel your heartbeat for a moment. A typical resting heart beats roughly once per second. Now consider, if you were to count every star in IC 1101 at the rate of 1 per heartbeat, 1 per second, without pause, without sleep, without stopping for any reason, how long would it take to finish? 100 trillion seconds. That is the total. Divided by the number of seconds in a year, roughly 31.5 million, the answer is approximately 3,170,000 years, more than 3 million years of counting without a single pause. 3 million years ago, the Earth did not have modern humans. The genus Homo had barely emerged. The earliest stone tools were just beginning to appear in the archaeological record. No language existed. No fire was controlled. No word for star had ever been spoken by anything that would be recognizable as human, and you would still be counting. That is what 100 trillion means when you hold it against human time. IC 1101 holds that many suns inside it, each one a coherent, gravitationally stable nuclear reactor, burning for millions or billions of years, many of them almost certainly circled by worlds. You might sit with that for a moment. 100 trillion is not a number that belongs on a page. It belongs in a long, quiet pause. The stars of IC 1101 are not like the Sun. They are, on average, far older. The galaxy stopped forming new stars long ago. Its supply of cold gas, the raw material of star formation, was exhausted through billions of years of mergers and the heating effects of its central black hole. What remains is an ancient stellar population, rich in heavy elements, burning at the low, slow temperatures of red and orange giant stars and of small, cool main-sequence dwarf stars that will outlive the current age of the universe by orders of magnitude. The galaxy glows amber in long exposure images, not the blue-white of active star formation, but the deep, warm colour of ancient nuclear burning, 7-billion-year-old stars and older light that left its sources before the Earth and Sun existed, crossing 1 billion light-years to arrive at our instruments tonight. This is a galaxy that has already lived most of its life as an active, growing structure. What we observe now is a relic, vast, luminous, extraordinary, but no longer building. At the centre of IC 1101 lives one of the most extreme objects ever measured, the Milky Way's central black hole, Sagittarius. A star carries a mass of approximately 4 million solar masses, 4 million times the mass of our Sun, compressed into a region smaller than the distance from the Sun to Mercury. That is considered a moderately sized, supermassive black hole for a galaxy of our scale. The black hole at the centre of IC 1101 carries an estimated mass of between 40 and 100 billion solar masses. The range is large because the measurement is genuinely difficult at this distance. But even the lower bound of 40 billion solar masses is 10,000 times more massive than Sagittarius A star. The upper bound of 100 billion solar masses would make it among the most massive black holes in the known universe. For context, our Sun has been burning for 4.5 billion years and will burn for another 5 billion. If you converted the entire mass of our Sun, not the energy it produces, but its entire physical mass, into pure energy, according to Einstein's mass-energy equivalence, you would get a number too large for any human application to use. The black hole at IC 1101 contains the gravitational equivalent of between 40 billion and 100 billion of those. Astronomers classify black holes above about 10 billion solar masses as ultramassive. By that standard, the object at the centre of IC 1101 sits at or very near the theoretical upper boundary of what can exist. How does a black hole grow this large? Almost certainly through the same mechanism that built the galaxy around it. Merger after merger, consuming not just gas and stars but entire galaxies, swallowing their central black holes as well, combining their masses and growing with each collision. The smoothness of IC 1101's halo, the lack of the sharp features you would expect from recent dramatic events, suggests that most of those mergers happened early, billions of years ago, and that the halo settled into its current diffuse, featureless shape over an enormous span of time. And now, with IC 1101 fully in view, we can ask the question the 2022 discovery of Alcyoneus made unavoidable. Which one is larger? The answer, it turns out, depends entirely on what you mean by the word galaxy, and that definitional choice turns out to reveal something more interesting than any single number. Alcyoneus's radio lobe spanned 16 million light-years. Nothing else built by a single galaxy comes close to that. In terms of the total spatial extent of a single galactic structure, Alcyoneus holds the record without serious challenge. But Alcyoneus's stellar body, the actual collection of stars at its centre, spans roughly 240,000 light-years, about twice the Milky Way, entirely unremarkable by galactic standards. Its star count is far below average for a giant radio galaxy. Its black hole, at roughly 390 million solar masses, is nearly 100 times less massive than the lower estimate for IC 1101's black hole. IC 1101, by contrast, contains 100 trillion stars, roughly 500 times more than Alcyoneus's stellar body. its black hole may outmass Alcyoneus's by a factor of more than 10,000. Its stellar halo, at 4 million light-years in diameter, exceeds the size of Alcyoneus's stellar body by a factor of about 17. Two objects, both record holders, neither simply bigger than the other. Alcyoneus is the largest single structure produced by a galaxy. IC 1101 is almost certainly the most massive, most star-rich galaxy ever measured. These are not the same claim, and the fact that they are different claims is the point. The universe, it turns out, has more than one way to be enormous, and the two ways produce structures so different in character that comparing them directly requires deciding which dimension of enormity you care about most. Science does not have a simple answer to which is the biggest galaxy, and that is not a limitation of the science. It is a genuine reflection of what the universe offers, objects so diverse in their extremity that our single-word questions cannot contain them. But the comparison between Alcyoneus and IC 1101 raises a question that neither object alone would prompt. IC 1101 grew to what it is through a specific process, a process that has been operating at galactic scales since the universe was young, merger after merger, galaxy after galaxy consumed, a history of collisions stretching back billions of years, each one adding mass, adding stars, adding to the halo, deepening the gravitational well at the center. Galaxies, it appears, become monsters through the same mechanism that structures everything at the largest scales. Gravity pulling matter toward other matter, smaller things falling into larger things, and the largest things becoming so dominant that everything nearby eventually joins them. But how exactly does this process work? And what determines whether a galaxy grows to have 100 trillion stars, or grows instead to fire jets 16 million light-years across an intergalactic void? What makes IC 1101 one kind of titan and Alcyoneus another? The answer begins not with the galaxies themselves, but with the invisible architecture they were born inside. Two galaxies are approaching each other. They have been approaching for billions of years, drawn together by the one force in the universe that has no off switch and no ceiling. Neither one can stop, neither one is trying to, and what will emerge from their encounter tens of millions of years from now will bear almost no resemblance to either of them today. Right now, the Andromeda Galaxy is falling toward us, not drifting, not moving in the ambient way that galaxies shift through expanding space. Falling, pulled by gravity, closing the distance between us and our largest galactic neighbor at roughly 110 kilometers per second. About 68 miles per second, fast enough to cross the continental United States in under a minute. At that speed, in approximately 4 to 5 billion years, the Milky Way and Andromeda will collide. What does that mean for the trillions of stars involved? What happens to the planets in their orbits? What emerges on the other side? The answer reveals the mechanism behind every giant galaxy that has ever existed, including IC 1101, including, almost certainly, whatever galaxy Alcyoneus will become if its jets ever finally go quiet and gravity takes over from plasma. And the answer is far stranger than the word collision suggests. The word collision implies impact, objects striking each other, transferring energy, shattering. But a galactic collision is something else entirely, something that only becomes comprehensible once you understand how empty a galaxy actually is. Consider the nearest star to our Sun, Proxima Centauri, about 4¼ light-years away. That distance, 4¼ years of light-speed travel, is the typical separation between stars in our galaxy. The stars themselves are tiny compared to that gap. Our Sun is about 1.5 million kilometers, about 900,000 miles, in diameter. The distance between stars is roughly 40 trillion kilometers, or 25 trillion miles. If you shrank the Sun down to the size of a grain of sand, roughly 1 millimeter across, the nearest neighbouring grain of sand would sit about 27 kilometres, or 17 miles away. Empty space in every direction for 17 miles, and then another single grain of sand. That is how sparsely populated a galaxy is. When two galaxies merge, their stars do not crash into each other. The probability of any individual star physically striking another during a full galactic collision is vanishingly small, less than 1 in a billion in most models. What actually happens is that two vast, almost entirely empty gravitational systems interpenetrate each other in near-perfect silence. The stars pass through the combined structure like two swarms of fireflies passing through each other on a dark night, close enough to feel the gravitational tug, but almost never close enough to actually touch. What does collide? Dramatically, chaotically, and consequentially, is the gas. But before the stars, before the gas, before any of the visible structure of a galaxy, something else collides first. Something that cannot be directly seen at all. Every galaxy exists inside a dark matter halo. A dark matter halo is an enormous sphere of invisible matter, matter that does not emit light, does not absorb light, and interacts with ordinary matter only through gravity, that surrounds and interpenetrates the visible galaxy like a vast, transparent bubble. The dark matter halo of our own Milky Way is estimated to extend somewhere between 300,000 and 500,000 light-years in radius. That is 3 to 5 times the radius of the visible stellar disk we call home. Picture this. Imagine two soap bubbles slowly pressing toward each other. Before their visible surfaces make contact, the gas pressure fields they each carry begin to deform each other. The bubble's outer boundaries begin to distort, elongate, and eventually merge, long before any dramatic change is visible to a casual observer. Dark matter halos behave similarly. Before two galaxies make any visually dramatic approach, their halos have already begun to interact, gravitational tides reaching across millions of light years, slightly distorting the outer edges of each halo, creating long filamentary streams of dark matter connecting the two systems. By the time the galaxy's visible stellar bodies are close enough to show obvious mutual distortion, the warped edges and long tidal tails seen in Hubble images of colliding galaxies, the dark matter halos have already been merging for a very long time. The dark matter scaffold sets the stage for everything that follows. The merger of halos determines the depth of the combined gravitational well. That depth determines how much gas falls inward. That gas determines the burst of star formation, and the degree of that burst, combined with the energy released by the merged central black holes, determines the final character of whatever galaxy emerges. When two gas-rich galaxies like our own Milky Way, full of cold molecular gas, actively forming stars, merge, the collision triggers one of the most productive events in the universe. The gas from both galaxies, unlike the stars, physically collides. Two vast clouds of cold hydrogen slamming into each other, compressing, heating, fragmenting. The sudden compression of gas triggers a starburst, a period of star formation so intense that a galaxy can form more new stars in a few 100 million years than it would normally create in several billion. These short, fierce periods of creation are some of the brightest events in the observable universe. Galaxy mergers in the early cosmos blazed with light from newly born stars at rates that can exceed our galaxy's current star formation rate by factors of 10, 100, sometimes more. But mergers are also destructive in a specific and irreversible way. The collision funnels enormous quantities of gas toward the centers of both galaxies and toward the supermassive black holes waiting there. The black holes feed voraciously on this sudden inflow. The accretion rates spike. Energy pours outward from both active galactic nuclei, superheating surrounding gas, driving winds and jets through the galaxy's interior, blasting material out of the system altogether. Here is where a genuinely unresolved question in astrophysics sits, and it is worth pausing on. How exactly does the central black hole's energy output end a galaxy's ability to form stars? Two mechanisms are well documented in observations, and researchers debate their relative importance. In the first, sometimes called the quasar mode, the black hole accretes rapidly during the merger, releasing enough energy through winds and radiation to heat and eject the cold gas from the entire galaxy in a relatively short, violent burst. In the second, sometimes called the radio mode, the black hole settles into a lower accretion rate after the merger and fires jets that inflate bubbles of hot plasma through the galaxy's halo, slowly and continuously heating the incoming gas before it can cool, condense, and form stars. Both mechanisms are observed in real galaxies. Which one dominates for a given galaxy and how they interact remains one of the active frontiers of galaxy evolution science. What science does agree on is the outcome. Cold gas, the raw material of star formation, is removed, heated, or expelled. The galaxy's spiral structure, if it had one, is scrambled by the collision into a smooth, featureless ellipsoid. The two central black holes spiral together and eventually merge, releasing gravitational waves as they coalesce. And what remains is a galaxy that can no longer build stars at any significant rate, red from its old stellar populations. Still, ancient, a relic of every collision that made it. Astronomers sometimes call these objects red and dead. The phrase is deliberately stark. The star-forming phase of a galaxy's life, the period when it is actively building itself, converting gas into suns, creating the possibility of planets and chemistry and time, ends permanently. IC 1101 is what this process looks like when it has been running, uninterrupted, for longer than our Sun has existed. The smoothness of its outer halo, the way it fades with extraordinary gradual evenness from its blazing center outward, tells astronomers that the mergers that built it happened mostly early in the universe's history. The absence of sharp features, the lack of tidal streams or irregular structure in the outer regions all point toward a formation epoch likely 10 to 12 billion years ago. Our solar system would not form for another 5 to 7 billion years. The planet you are sitting on tonight did not exist. The atoms in your body had not yet been assembled by any star, and IC 1101 was already consuming galaxies, merger after merger after merger, each one adding stars, each one delivering another central black hole to be absorbed into the growing ultramassive object at the center, each one contributing to the vast diffuse halo that eventually extended its gravity across millions of light years, sweeping up the smaller galaxies of the Abell 2029 cluster as they fell inward under the combined gravitational pull of all that accumulated dark matter. The lack of other large luminous galaxies at the center of Abell 2029, the peculiar emptiness of the cluster's interior, given how dense its outer regions are, suggests that IC 1101 consumed them, all of them, absorbed their stars into its growing halo, merged their black holes into its own, stripped their gas, and scattered it as intra-cluster light. Individual stars drifting free in intergalactic space, no longer bound to any galaxy, belonging only to the cluster as a whole. The Wikipedia entry for IC 1101 uses the phrase chewed up. It is uncharacteristically vivid language for a scientific resource, but it captures something real. The galaxy grew by consumption over a timescale that encompasses more than 2/3 of the universe's current age. We should pause on something that is easy to overlook. We are living in a moment in cosmic time when IC 1101 is still visible to us. Still close enough, 1 billion light years, that our telescopes can resolve it in enough detail to measure its core structure, its stellar velocity dispersion, its halo extent. The Hubble Space Telescope has imaged it. Chandra has mapped its X-ray emissions. We know what its center looks like, roughly how massive its black hole is, how its halo deforms with distance. Astronomers calculate that in the very far future, tens of billions of years from now, the accelerating expansion of the universe will carry galaxies like IC 1101 beyond the cosmological horizon. Their light will redshift to undetectable frequencies. Their existence will become, in principle, unknowable to any civilization that arises after a certain point in cosmic time. The evidence for a universe full of distant, massive galaxy clusters, the very evidence we are using tonight to understand what galaxies become, will simply not be available to any intelligence that arises late enough. We are early. We can still see it. That is not a small thing. And you are part of this process too, not metaphorically, but physically. The Andromeda Galaxy falling toward us at 68 miles per second will, in 4 to 5 billion years, produce a collision whose outcome almost every model predicts will be a large, slowly rotating elliptical galaxy. No spiral arms, no ongoing star formation, old, red, and vast. The Milky Way and Andromeda will lose their individual identities and become something new, something larger, quieter, and far less suited to the kind of ordered disk structure that allowed a star like our Sun to form in a stable orbit for 4.5 billion years. This is the process that built IC 1101. The same gravity, the same merger dynamics, the same outcome written in what will eventually become of the galaxy you call home. But IC 1101 and Alcyoneus did not become what they are purely through the mechanics of individual mergers. Something larger than any galaxy shaped them both. Something that determined where they formed, what fell toward them, how much material was available over the billions of years of their growth. The universe is not a uniform field of matter and gravity. At the very largest scales, scales that make both of these galaxies look small, it possesses a structure, a network, an architecture of filaments and voids, so enormous that clusters like Abell 2029 are merely nodes within it. Cities are intersections in a web that spans hundreds of millions of light years. And Alcyoneus sits inside that web in a way that may explain everything we have not yet been able to explain about it. The jets that grew too large, the structure that broke every model, the engine that should not have produced what it did. To understand why Alcyoneus is what it is, we need to step back further than any galaxy. We need to look at the shape of the universe itself. Step back, further than any chapter has taken us before, further than any galaxy, further than any cluster, far enough that Alcyoneus, 16 million light-years across, the largest known structure built by any single galaxy, shrinks to something too small to see in the frame. At this scale, something else comes into view. The universe is not randomly distributed. That sentence seems simple. It is, in fact, one of the most profound things cosmology has ever confirmed. And the full weight of what it means only becomes visible at a scale so large that everything we have discussed until now, including Alcyoneus, including IC 1101, including the Abell 2029 cluster, and all the thousands of galaxies it contains, would register as a single dot at the resolution we need to see it. At the largest scales, matter in the universe arranges itself into a structure, a network of filaments, long threads of dark matter and gas stretching for hundreds of millions of light years, connecting dense nodes where galaxy clusters pile up at their intersections. Between the filaments, vast empty voids, almost nothing, regions of space so depleted of matter that they stretch 300 million light-years across and contain almost no galaxies at all. Together, this structure is called the cosmic web, and it is, by any measure, the largest coherent pattern that exists in the observable universe. Alcyoneus lives inside it, and where it lives, specifically, which filament, how far from the nearest dense node, may be the answer to the question we have been building toward since the first chapter. The cosmic web did not form after galaxies. Galaxies formed because of it. In the earliest moments after the Big Bang, the universe was almost, but not perfectly, uniform. Quantum fluctuations during inflation left behind tiny differences in density, regions that were a fraction of a percent denser than their surroundings. The differences were negligibly small. But gravity is patient. Over hundreds of millions of years, those slightly denser regions pulled in surrounding matter. The denser a region became, the more gravity it commanded. The more gravity it commanded, the faster it accumulated mass. Dark matter, the invisible, gravity-obeying substance that constitutes roughly 85% of all matter in the universe, responded first. Dark matter cannot form stars or emit light, but it feels gravity precisely the same as ordinary matter, and it moves in response to it without any of the pressure or friction that slows down gas. So dark matter began assembling into a vast three-dimensional web first, long before the first star ignited anywhere in the universe. Sheets and filaments of dark matter formed over hundreds of millions of years in the cosmic dark, invisible structure growing in the absence of any light. Ordinary matter, gas, the hydrogen that would eventually become stars and planets and people, followed the dark matter inward, not because it was attracted to the dark matter directly, but because both were responding to the same gravitational landscape. The dark matter had already carved out the valleys and ridges. The gas simply flowed downhill into them. Picture this. You are looking down at a large city from altitude at night. Clusters of bright light sit at major intersections. Thinner threads of streetlight connect them, stretching across the darkness. Between the lit roads, wide dark spaces where almost no light falls. The cosmic web at the scale of hundreds of millions of light years looks precisely like this, but inverted in significance. The bright nodes are galaxy clusters. The threads between them are cosmic filaments, each one containing more dark matter than thousands of Milky Ways. And the dark spaces between the threads are voids, not the darkness of a city park, but near total absence, hundreds of millions of light years across, where almost no galaxy has ever formed. Let us pause on scale. The Milky Way spans 100,000 light years. Alcyoneus spans 16 million, 160 Milky Ways. IC 1101's stellar body spans 500,000 light years. Able 2029 spans 8 million light years. A single cosmic filament can span several hundred million light years from end to end. Let us do the comparison directly. Take Alcyoneus, the entire 16 million light-year extent of the largest known radio structure ever measured. Now slide it against a single filament. The filament is, at a conservative estimate, 10 to 15 times longer. Alcyoneus, measured against the thread it lives inside, is roughly what a single skyscraper is measured against the full length of the Amazon River. And yet, even that comparison understates the disproportion in a different direction. Because a filament is not just long. A filament is a region of three-dimensional space containing more matter than the human mind has any natural framework to accommodate. Current cosmological simulations, including recent work from the Millennium TNG project at the Max Planck Institute for Astrophysics, suggest that over 50% of all the matter in the universe, the majority, exists not in galaxies, not in galaxy clusters, but in the intergalactic medium within and around cosmic filaments, spread thin across hundreds of millions of light years, nearly invisible, almost impossible to directly detect with most instruments, but present, continuously, threading through everything. Alcyoneus sits inside one of those threads. Think about the air around you right now. Take a breath. The air in your lungs contains roughly 10 billion trillion molecules in every breath. Nitrogen, oxygen, water vapor, trace gases, all packed together in a relatively dense, warm medium that supports life. Now imagine removing almost all of that. Not all, almost all. One molecule remaining for every cubic meter of space, then one for every 10 cubic meters, then one for every 100. Continue until the remaining gas is so thin that a human body could never detect it through any sense we possess. Continue until the density is so low that the distances between individual atoms are measured in centimeters. That is the warm, hot intergalactic medium, the gas that fills the space between galaxies inside cosmic filaments. not empty space, not a vacuum, but a gas of unimaginable thinness, heated to temperatures of between 100,000 and 10 million degrees Celsius by the energy released over billions of years by galaxies, black holes, and galactic mergers. So hot it cannot cool and form stars. So thin it cannot be detected by most instruments, and yet extending continuously through cosmic filaments for hundreds of millions of light years, constituting a substantial fraction of all the ordinary matter in the observable universe. This is the medium Alcyoneus's jets are pushing into. This is the material that shapes the lobes, the invisible partner in the slow dance. The confirmed position of Alcyoneus within a cosmic filament, established in Martijn Oe's 2022 paper by a galaxy number density analysis of the region, matters enormously for the question that has been sitting unanswered since Chapter 1. Why did a below-average engine build the largest known radio structure? The leading hypothesis, developed by OEI and his team, and still the most credible explanation in the published literature, centers on density. The intergalactic medium inside cosmic filaments is not uniform. Some sections of filaments are denser, closer to the filament's spine, near intersections with other filaments, in regions where matter has been flowing inward for longer. Some sections are thinner, further from the filament's center, in quieter regions where fewer galaxies reside, and the intergalactic medium has been more slowly assembled. Alcyoneus does not sit at the intersection of filaments where a galaxy cluster would be expected, and where the surrounding medium would be dense. The nearest galaxy cluster to Alcyoneus lies, at current estimates, over 11 million light-years, about 3.4 megaparsecs, away in co-moving distance. Alcyoneus sits in a stretch of filament that appears to be exceptionally low in density compared to other giant radio galaxies studied at comparable scales. And here is why that matters. The jets of a radio galaxy are not firing into a perfect vacuum. They are pushing against the warm, hot intergalactic medium, fighting its pressure as they expand outward. The more dense the surrounding medium, the more resistance the jets encounter, the sooner the lobes stall and cease their expansion. The thinner the surrounding medium, the less resistance, and the further the lobes can travel before the jet's energy is finally exhausted. Alcyoneus's lobes carry the lowest pressure measurements ever recorded for any radio galaxy, not slightly below average, the absolute minimum, 5 times 10 to the negative 16 pascals, a pressure so close to nothing that ordinary laboratory equipment could not replicate it. This is the signature of plasma that has expanded almost without resistance into an exceptionally thin intergalactic medium, spreading and thinning as it goes, filling an enormous volume of nearly empty space. The cosmic web gave Alcyoneus the rarest of environments, a position inside a filament, with its steady supply of infalling gas to power the central black hole, but surrounded by intergalactic medium too thin to slow its jets. Imagine standing outside the observable universe, a perspective that no physical object can occupy, but that cosmological models allow us to reason about. Looking inward from an impossible vantage point, you would see the cosmic web spread across 13 billion light-years in every direction. Knots of blazing light where cluster after cluster sits at the intersections of filaments. Between them, the threads, pale, diffuse, stretching for hundreds of millions of light-years, carrying the majority of the universe's matter in a form too thin to see with any instrument we currently possess. And somewhere in one of those threads, one ordinary strand of the web, no brighter or thicker than 1,000 others, a small elliptical galaxy has been quietly firing 2 columns of plasma outward for hundreds of millions of years, building a structure 16 million light-years wide, enormous by any measure we have used, unmissable if you knew what to listen for, invisible from here, a rounding error in the geometry of the web that contains it. But Alcyoneus is not merely shaped by the cosmic web. The relationship runs in both directions. The Leiden University researchers noted something remarkable in their 2022 paper. The jets and lobes of radio galaxies expanding outward into the intergalactic medium of their host. Filaments heat that medium. The relativistic electrons deposited in the lobes, the magnetic fields stretched across millions of light years, the pressure waves propagating outward from the expanding plasma. All of this contributes energy to the surrounding gas, warming the intergalactic medium, changing its thermodynamic state, influencing the future flow of gas toward galaxies within that filament. A black hole of 390 million solar masses, a structure far smaller than a single solar system compared to the filament it inhabits, is, through its jets and their 16 million light-year consequences, contributing to the regulation of one of the universe's largest structures. The energy output of a single compact object influencing the temperature and density of a region hundreds of millions of times its own scale. The Leiden team offered a comparison. It is, they said, as if something the size of a marble regulates the temperature of the entire Earth. That image is not an exaggeration. The physics permits it. Alcyoneus demonstrates it. And here is the thing that makes all of this genuinely unsettling, not in a way that diminishes, but in a way that should make us lean forward. We have now traced Alcyoneus from its discovery in a reprocessed archive, a shape emerging from noise that no one had previously seen, through its radiophysics, its invisible engine, its position in the universe's largest structure. We have held the full chain of causality. Cosmic web filament determines environmental density. Environmental density determines how far jets expand. Jets determine the size of the lobes. The size of the lobes determines the record. And yet something in that chain still does not fully close. Alcyoneus is in a low-density filament environment, confirmed. But so are other giant radio galaxies that did not grow nearly this large. The environment matters, but the environment alone does not explain everything. Something about how long the jets have been firing and why they have continued firing for long enough to build a 16 million light-year structure without interruption. That question still does not have an answer our best models are confident in. And as it turns out, this is not the only place where our models break down. The deeper we look at the largest structures in the observable universe, the more clearly a pattern emerges. What we can explain and what we can observe have a gap between them. A gap that is not noise, not instrument error, not a matter of better data. A gap that suggests something fundamental about the universe may be missing from our understanding. The models that successfully predicted the large-scale structure of the universe, the abundance of hydrogen and helium in the cosmos, the temperature of the cosmic microwave background to extraordinary precision, those same models have a problem. Several of them, in fact. And they are not small. Science does not have all the answers. That sentence is obvious in principle. Every honest scientist would say it. But there is a difference between "we do not yet know everything," which applies to every field, always, and our best models produce predictions that directly contradict our most precise measurements. The first is comfortable, the second is not. In cosmology, the science of the universe at its largest scales, we are presently living through something that belongs to the second category. Not one problem, several, and the objects we have been discussing throughout this entire journey are sitting at the intersection of some of the most serious unresolved tensions in modern physics. Alcyoneus is not simply a record holder. Alcyoneus is a problem. Not because we cannot measure it. We have measured it with extraordinary precision across 3 independent datasets. But because what we have measured, when placed against the theoretical framework that governs our understanding of how the universe works, produces contradictions that no current model fully resolves. This is not a reason for alarm, but it is a reason to pay attention. The framework at the center of modern cosmology carries the name Lambda CDM. Lambda refers to the cosmological constant, the mathematical term representing dark energy, the mysterious component driving the accelerating expansion of the universe. CDM stands for cold, dark matter, slow-moving, gravity-following, invisible matter that constitutes the scaffolding of all large-scale structure. Together, lambda CDM constitutes the most precisely tested physical theory in the history of cosmology, using only 6 free parameters, 6 numbers that describe the fundamental properties of the universe. It correctly predicts the temperature variations in the cosmic microwave background, the large-scale distribution of galaxies across the observable universe, the abundances of hydrogen and helium created in the minutes after the Big Bang, and the rate at which galaxy clusters formed and grew over billions of years. 6 numbers, a 13.8 billion year universe, predictions accurate to fractions of a percent. The theory works extraordinarily well at the scales it was built to describe, but at other scales, and around objects like Alcyoneus, something starts to strain. And here is where the story becomes genuinely interesting. The universe is 13.8 billion years old. That is a long time, longer than the Sun, the Earth, and the entire history of life on this planet. But in the context of what Alcyoneus required to build itself, 13.8 billion years is a constrained budget. Radio galaxies grow by firing jets continuously. The lobes of Alcyoneus, 16 million light-years from end to end, required those jets to fire without interruption for what the best current estimates suggest could be hundreds of millions of years. That is a long time by any human measure, but it is not obviously easy to achieve within a universe that is only about 13.8 billion years old, and in which the process of galaxy formation itself took hundreds of millions of years to begin. Consider the timeline. The first stars formed roughly a few hundred million years after the Big Bang. The first galaxies assembled over the following hundreds of millions of years. Supermassive black holes at their centers began accreting and growing. Only then, after all of that prior formation, could a black hole like Alcyoneus's have begun firing jets at all. This means that whatever process produced Alcyoneus's 16 million light-year structure had to operate for long enough, continuously enough, in an environment cooperative enough to build that structure within a universe that was already middle-aged when the process began. Not impossible, but not trivially explained either. And our models do not reliably predict the specific combination of conditions required to produce something of this scale within the available time. And here is where a second problem compounds the first. Alcyoneus has been firing jets into intergalactic space for what appears to be an extraordinary duration. Those jets carry energy. That energy heats the surrounding gas, the warm, hot intergalactic medium filling the cosmic filament Alcyoneus inhabits. Heated gas does not cool easily. Gas that cannot cool cannot flow inward toward a galaxy. Gas that cannot flow inward cannot fall toward a black hole, and a black hole that is not being fed cannot maintain the accretion rate that powers its jets. In other words, the jets should be shutting themselves off. The more effectively they fire, the more they heat the surrounding medium, the less gas falls inward to sustain them. This self-regulating loop, called AGN feedback, is not a theoretical invention. Astronomers observe it operating in galaxy after galaxy. A black hole fires jets, heats the surrounding gas, the gas stops cooling, the jets lose their fuel supply and switch off. The gas slowly cools again, falls inward, the jets restart. On and off. Cyclically, self-regulating. For typical giant radio galaxies, this cycle operates on timescales of tens to hundreds of millions of years. The jets run for a while, quench, restart. The radio lobes from one cycle may still be detectable as the black hole enters its next episode. Multiple episodes, separated by gaps, accumulate into the structure we observe. But Alcyoneus has the lowest low pressures ever measured for any radio galaxy. Its plasma has expanded almost without resistance across 16 million light-years. A signature of continuous growth, not episodic activity interrupted by gaps. The structure does not easily resemble the result of multiple, interrupted cycles. Picture this: a ship's navigator trying to chart a coastline by examining individual grains of sand under a microscope. Every grain is precisely measured, but the resolution at which they are working is so far from the scale of the coastline that what appears in the microscope tells them almost nothing about the shape of the shore. Current cosmological simulations face an almost identical problem when trying to model Alcyoneus. The physics of jet formation and propagation operates on scales measured in astronomical units, the distance from the Earth to the Sun. The structure those jets produce spans 16 million light-years, roughly 1 trillion times larger. No simulation in existence can resolve both ends of that range simultaneously. Researchers at institutions including Leiden University, the Max Planck Institute, and Johns Hopkins have confirmed that the full chain of physical processes, from black hole to megaparsec lobes, remains one of the greatest unsolved problems in astrophysics, as noted in a 2023 review from the University of Hertfordshire. Simulations use approximations, small sets of rules that substitute for the physics they cannot resolve directly, and those approximations, reviewed across the major simulation suites, consistently fail to produce structures as large as Alcyoneus in the frequencies at which they are observed. This does not mean Alcyoneus cannot exist, we have measured it, but it does mean that our models, as currently constructed, do not reliably produce it. And the problem, as it turns out, extends beyond radio galaxies. The standard model of cosmology, lambda CDM, has, in the past decade, developed a tension that has resisted every attempt at resolution. Two independent methods of measuring the universe's current expansion rate give results that disagree at a level of statistical confidence that, in any other scientific context, would be considered overwhelming evidence of a genuine discrepancy. When cosmologists use the cosmic microwave background, the faint light left over from the universe's infancy, mapped with extraordinary precision by the European Space Agency's Planck satellite, to infer the current expansion rate, they arrive at a value of about 67.4 kilometers per second per megaparsec. That unit is a measure of how fast space itself is expanding between any 2 points, separated by 3.26 million light-years. In plain terms, it describes the speed at which the universe is stretching. When astronomers measure the expansion rate directly, using well-understood standard candles like Type 1a supernovae and Cepheid variable stars, a method refined over decades by teams including the SH0ES collaboration, led by Nobel laureate Adam Rees at Johns Hopkins, they arrive at a value closer to 73 kilometers per second per megaparsec, a difference of roughly 5 to 6 kilometers per second per megaparsec. That sounds small, but 5 sigma, the statistical threshold reached by multiple independent measurement teams, is the level at which particle physicists declare a new particle discovered. The discrepancy is not noise. The measurements have been checked against each other, verified by independent methods, confirmed using data from the James Webb Space Telescope. The two values do not agree. Scientists call this the Hubble tension, and it remains, as of today, genuinely unresolved. Two schools of thought exist, both presented fairly in the published literature. The first holds that a systematic error, some undetected bias in one or both measurement chains, is hiding somewhere in the mathematics, waiting to be found, and that when it is discovered, the values will converge. The second holds that both measurement chains are correct, and that the discrepancy reflects something genuinely missing from our understanding of physics. New particles, an unexpected phase of dark energy in the early universe, a modification to general relativity on cosmological scales. Science does not know which is right. Adam Rees himself has stated directly, the discrepancy suggests that our understanding of the universe may be incomplete. That is not a casual comment. That is a Nobel laureate sitting with measurements he cannot explain. We do not know. Not just about Alcyoneus, not just about the feedback paradox, about the expansion rate of the universe itself. And this is not a failure. This is the frontier. Every time in the history of science that a measurement failed to fit its model, truly failed after systematic errors were exhausted, something new eventually emerged. The precession of Mercury's orbit, which Newtonian mechanics could not account for, presaged general relativity. The unexpected faintness of distant supernovae, which no prior model had predicted, revealed the accelerating expansion of the universe and dark energy. The anomalous rotation curves of galaxies, which should not have been possible under the visible matter budget, pointed toward dark matter. Each gap between model and measurement held open honestly rather than papered over, eventually became a window. What Alcyoneus offers is another window. Not because we understand it, but precisely because we do not. A structure this large, produced by an engine this ordinary, growing in an environment this thin, resisting every standard explanation for why it should have been able to build what it built, represents the kind of anomaly that, historically, precedes revision. You are living in the specific moment when the data is in and the explanation is not. That is not a moment of anxiety. That is a moment of privilege. The generation of scientists working on these questions right now, at Leiden, at Max Planck, at Johns Hopkins, at Oxford, at institutions whose contributions we cannot yet predict, will either find the explanation within the existing framework, or they will find something that changes the framework. Either outcome advances what we understand about where we are, and here is the thing that has been quietly waiting throughout all 8 of these chapters, patient and unrushed. We have followed Alcyoneus from discovery to measurement, from radio waves to jet physics, from the cosmic web to the limits of our models. We have learned what it is, what powers it, where it lives, and why it challenges everything we thought we knew about how large a single galaxy's influence could reach. But we have not yet sat with what it means, not the physics, not the models, the actual human meaning of living in a universe that contains something this vast, and of being the kind of species that, from a small rocky planet orbiting an unremarkable star in a mid-range galaxy, found it. Because that, in the end, may be the most remarkable thing in this entire story. Everything we have discussed, every measurement, every structure, every galaxy and black hole and filament, is the past. We have not been looking at the universe. We have been reading its history. And that distinction, quiet as it is, changes everything. The night around you right now contains more than darkness. The air in the room where you are sitting or lying has a specific quality, a weight, a temperature, a stillness that feels at this hour different from any other time of day. Something about the night makes it easier to hold large thoughts. Human attention has always turned outward in the dark. Every civilization that has ever existed has looked up at the same sky from their particular patch of ground and tried to understand what they were looking at. None of them understood what they were actually seeing, not because they were unintelligent, but because the answer to what they were seeing requires a fact that took humanity a very long time to fully grasp, and that even now, stated plainly, has the quality of a small, permanent shock. Light takes time to travel. The light from the sun takes approximately 8 minutes and 20 seconds to reach us. So the sun you see when you look up during the day is not the sun as it is now. It is the sun as it was 8 minutes and 20 seconds ago. The light from Proxima Centauri, our nearest stellar neighbour, takes about 4¼ years to reach us. The light from the centre of the Milky Way takes approximately 26,000 years. And the light from Alcyoneus, the structure we have spent this entire journey learning to understand, left its source 3 billion years ago. 3 billion years. At that time, the most complex life on Earth was still single-celled. No animal existed anywhere on this planet. Not one. The oxygen in the air we breathe had not yet been produced in anything like its current abundance. The world outside your window tonight would have been unrecognizable to any sense you possess, and the light we receive from Alcyoneus departed before any of that changed. This is the fact that transforms everything else we have learned. We do not observe the universe as it is. We observe the universe as it was, at a different time for every distance, a different chapter of cosmic history encoded in every wavelength we receive. The closer an object, the more recent the light. The further an object, the further back in time we are seeing. The observable universe is not a snapshot of the present. It is a layered archive, a library of the past arranged by distance, with the oldest light arriving from the furthest edges. When Martijn Uy's team examined the LOFAR data and found Alcyoneus's lobes resolved against the sky, they were reading a message written 3 billion years ago by electrons spiraling through magnetic fields in plasma lobes that are, by now, almost certainly different from what we measured. The Alcyoneus we know is the Alcyoneus of 3 billion years ago. Whether it has grown since, whether its jets have finally quieted, whether the structure is larger or smaller or differently shaped in the universe's actual present, we cannot know. The universe's present is not accessible to us, only its past. And I think it is worth sitting with that for a moment, because it means that every object we have discussed, Alcyoneus, IC 1101, the Able 2029 cluster, every galaxy in every survey ever conducted, all of them are historical documents. We are not astronomers of the present, we are archaeologists of the cosmos. Everything we know about the universe's largest structures is knowledge of where they were and what they were doing at specific moments in the past. The universe's actual present is invisible to us, silent, unreachable. And yet, from this small, warm planet, using instruments we built in the last century, we found it anyway. Let us do the comparison one final time, carefully and without rushing. The Milky Way is 100,000 light-years across. That is an enormous distance by any human measure. Walking across it at a comfortable pace, 40 kilometers or 25 miles per day, would take over 64 trillion years. The universe has only been around for 13.8 billion years. Even driving at highway speed continuously without pause, crossing the Milky Way would take over 1 trillion years. By the time you arrived, our sun would be long dead. Alcyoneus's radio structure is 160 times wider than that. Not 160 Milky Way galaxies stacked side by side. A single continuous structure built by one black hole in one galaxy, over what are likely hundreds of millions of years of continuous activity. 160 times the width of everything that contains our home, our sun, the 400 billion stars that make up the galaxy we live in. One continuous structure that we found from here using radio waves. And IC 1101 sits inside a galaxy cluster spanning 8 million light-years and contains 100 trillion suns, 500 times more than our galaxy, and has been passively aging for billions of years. Its ancient stellar population burning slowly in colors our eyes would register as deep amber and copper, its ultra-massive black hole sitting dormant at the center of a structure that consumed dozens of galaxies to become what it is. Every star in IC 1101 is a sun, each one potentially circled by planets, each one a nuclear furnace burning for billions of years. Consider what 100 trillion of them means for one question that human civilization has never stopped asking. The Milky Way, with its several hundred billion stars, likely hosts hundreds of billions of planets, perhaps more. If IC 1101's 100 trillion stars are even remotely similar in their planetary systems, the number of worlds it may contain is a figure that no human language has a natural frame for. Not millions of planets, not billions, trillions, a structure that could contain, in principle, more worlds than all the words ever spoken in all the languages, in all of human history could count. And yet, IC 1101 itself, at 4 million light-years across, is smaller than the width of a single cosmic filament. And cosmic filaments are themselves thin threads in the web that fills the observable universe. The human brain was not shaped by evolution to understand any of this. Our intuitions were calibrated for the scale of an East African savanna, perhaps a few hundred kilometers in any direction, timescales of decades, quantities in the hundreds or thousands. The neural machinery that processes spatial relationships, duration and number was never subjected to evolutionary pressure from anything requiring it to grasp a billion light-years, or 100 million years, or a number with 15 zeros. We are working at the absolute edge of what a biological mind can hold. And this is not a criticism of the mind. The fact that we can hold any of this, that we can construct abstract reasoning and mathematics that reach far beyond what our senses can directly perceive, that we can build instruments sensitive to radio waves our biology cannot detect, that we can process data from 3 billion light-years away and extract from it the shape and pressure of plasma lobes expanding through a cosmic web filament. That is the most extraordinary thing in this entire story. You could place a single human being against the scale of Alcyoneus, and the comparison would be so absurd it would vanish before the numbers resolved. A human body is roughly 1.5 meters, 5 feet, tall. Alcyoneus spans over 150 sextillion meters. The ratio between the two is so large that if you reduced Alcyoneus to the size of the Earth itself, a human being would still be invisible. Smaller than an atom, smaller than a proton, unmeasurably small. And yet the human being found it. That is not a small thing. That might be the most remarkable thing in the universe we have so far discovered. That matter arranged itself on one small planet in a configuration capable of looking at the rest of what matter made and understanding what it saw. Not perfectly, not completely, but genuinely, truly, with instruments and mathematics and years of careful, painstaking work by people who dedicated their lives to the question. In the first chapter of this story, we introduced a simple image, a beam of light setting out from one edge of Alcyoneus' structure, the kind of light we now understand as synchrotron radiation, produced by relativistic electrons spiraling through magnetic fields in plasma lobes built by a jet fired from an accretion disk surrounding a black hole of 390 million solar masses. That beam began its crossing of the 16 million light-year structure in the early Miocene epoch on Earth, when our genus had not yet appeared. No human hand had shaped anything. No word had ever been spoken. We have spent this entire journey learning what that beam has been crossing. We understand the plasma it moves through, the rarefied gas so thin that a human body would not be able to detect its presence by any sense we possess, yet continuous across millions of light years, carrying energy deposited there by jets that have been running longer than our planet has been alive. We understand the magnetic fields threading it, stretched by those same jets across structures so large they make the Milky Way look like a footnote. We understand the cosmic web filament surrounding it, one thread in the largest coherent pattern in the observable universe, containing more than half of all the ordinary matter that exists. We understand the problem it poses, why a beam like this exists at all, produced by an engine that should not have built something this vast, in an environment that researchers at Leiden and Oxford and Max Planck are still working to understand. We understand that it arrived here 3 billion years after it left its source as a faint radio signal at specific frequencies, and that a network of antenna arrays in a Dutch nature reserve, connected across a continent, finally read it. That beam of light is not just a fact about a distant galaxy. It is a record of everything the universe built in silence, over timescales that dwarf anything human civilization has ever attempted to measure, and a testament to the fact that something small enough to fit in a chair on a planet orbiting an unremarkable star found it, named it, and started to understand what it was. Take a moment here. We have travelled a long way together, from a Dutch PhD student's reprocessed data to the edges of what our best models can explain. You came here curious, and the universe answered with something stranger and more extraordinary than anything a curious mind could have invented. That is what the universe does, consistently, when we look carefully enough at it. You know more tonight than you did at the start. That matters. You are the only thing we know of in the observable universe that looked at Alcyoneus, that looked at any of this, and felt something about it. The structure does not know it exists. The cosmic web has no awareness of its own architecture. The plasma inside Alcyoneus' lobes spirals through magnetic fields with perfect physical indifference, no response to its own strangeness, no sense of the scale it represents, no understanding of what it took to find it. Only the species on the small planet noticed. Only the thing small enough to be invisible against the structure it studied had the capacity to be moved by it. The largest structures in existence formed silently over billions of years, without intent or awareness. Every thought, every life, every moment of joy or grief or curiosity or discovery that has ever occurred in all of human history unfolded inside something smaller than a rounding error at the scale of Alcyoneus. Every civilization, every war, every discovery, every person who ever loved another person or looked up at the sky and wondered what they were seeing, all of it contained inside what, at the scale we have been discussing, registers as nothing. And yet, the nothing looked up, the nothing asked, the nothing built instruments and ran calculations and found the something, and named it after a giant from mythology, because the human instinct, when confronted with something vast and inexplicable, is to give it a name and try to understand it. That instinct may be the most remarkable phenomenon in this 13.8 billion-year-old universe. We are not the largest thing here. We never were. We are not the oldest, or the most massive, or the most energetic. We are not the record holders by any physical measure that a radio telescope can take. But we are the ones who noticed. And that understanding, quiet, clear, earned by everything you have sat with tonight, is not insignificant. That understanding might be everything that matters. Think about what you did tonight. You sat quietly, in a room, on a planet, and you tried to understand something 16 million light-years wide. You followed a signal from a Dutch nature reserve to the edges of what physics can explain. You held black holes and plasma and dark matter and the shape of the universe itself. And you stayed. Most people never ask these questions. Most lives pass without ever reaching for a scale this large, or sitting with a mystery this honest, or feeling the particular kind of wonder that comes from realizing the universe is stranger and more beautiful than any story we could invent about it. You did that tonight, and here is what you carry with you now, out of this room and back into your life, the knowledge that the largest structure ever built by a single galaxy is sitting in the dark billions of light years away, still growing, still unexplained, still waiting for someone to understand it fully, that someone might be alive right now. They might be watching something like this, asking the same questions you just asked. The universe is still building, and we are still looking. That conversation between the infinite and the curious has been going on as long as there have been people. Tonight, you were part of it.